Alexander, an astronaut, is sent from the space station to fix an artificial satellite. He'd like to know his displacement. Alex then decides that it is best if once he ends his journey, he writes in the form of vectors the distance he's traveled. Conveniently for him, he can use the sun, the earth, the moon, and the space station as cardinal points. He then, once in the space station, writes the following.
Before seeing Alexander's calculations, here's a brief explanation of what a vector is and how to get them. In summary, a vector is a magnitude and a direction. A vector's magnitude can be obtained by its components of x and y. To know the magnitude, we can use the formula b equals square root of bx squared plus by squared. Vectors can be used to know the displacement of a journey. To do this, we need to know how to sum vectors. A sum of vectors is when out of two or more vectors, all of the components are added together and all of the y components are added together. With this new component, we can calculate the new distance of the new magnitude. Forget by the sum of vectors. Now, in order to know the direction of the vector, we use this formula. Angle is equal to tangent minus 1 times by over bx. But what if a vector is given, but its components aren't? Well, in that case, for you to know the components using the magnitude and the direction, you do as follows. Bx equals b times cosine of the angle and by equals b times sine of the angle. Though for this to work, you need to make sure that you are using real angles. A real angle is the angle formed by the vector if it were to be in the origin of a Cartesian plane, starting from the positive abscissa and following the order of the quadrants. Now that we know the theory, we can understand Alexander's procedure.
Vector 1 is composed of, as Alexander's notes state, a magnitude of 6 meters and a direction of 40 degrees from the moon to the earth. Alexander's first step is to get the real angle. To do this, it is simply just to imagine a floor protractor on a Cartesian plane. In this case, the moon will be 0 degrees and 360 degrees, the space station will be 90 degrees, the sun will be 180 degrees, and the earth will be 270 degrees. Now that we know this, by analyzing the instructions given by Alexander, we know that starting from the moon, 360 degrees, will travel 40 degrees towards the earth. So, 360 minus 40 equals 320. We know now that the real angle is 320. With this information, we can now proceed to solving for the x component using the next formula which was previously mentioned. Bx1 equals v times the cosine with the 0 degrees. Now we replace the values and solve with a calculator. So it's going to be Vx1 equals 6 times the cosine of 320 and Vx1 equals 4.6 meters. Now we solve for the y component. Vy1 equals v times the sine of 0. And then we will replace the values and solve with a calculator, and it will be 6 times the sine of 320 equals minus 3.86, and that is for vector 1. Now let's do the same for vector 2. Vector 2 has a magnitude of 3.6 meters and a direction of 25 degrees from the sun to the earth. Alexander gets a real angle by imagining the Cartesian plane. He then sums 270 minus 25, and this equals to 245. With this information of the real angle, he proceeds to get the components of the vector. Now we have the equation Vx2 equals v times the cosine of 0. Then he substitutes the value. Vx2 equals 3.6 times the cosine of 245. That equals minus 1.52. Then he proceeds with the component of y, and it's going to be v times the sine of the angle. And when we replace the values, is 3.6 times the sine of 245, which equals minus 3.26. He repeats this process with the rest of the vector.
Alexander will now obtain his displacement. He then sums all the components. Vx1 plus Vx2 plus Vx3 plus Vx4 plus Vx5 equals Vx. And the same for y. Replacing the values gives Alex Vx equals negative 3.76. Now for y, he replaces the values and it gives him Vy equals negative 8.31. With these components, he now uses them along with the Pythagorean theorem to find the magnitude of the vector or displacement. Vx squared plus Vy squared equals V squared. Now replacing the values gives him negative 3.76 squared plus negative 8.31 squared equals v squared. Now 14.14 plus 69.06 equals v squared. 83.2 equals v squared. V equals the square root of 83.2. V equals 9.12. Alexander is almost done now. He has discovered the magnitude of the vector, which is 9.12 meters. He's just missing the angle now, which he obtains with theta equal inverse tangent times Vy over Vx. Now replacing the values gives him theta equals equals inverse tangent times negative 8.31 over negative 3.76. Now theta equals 65.65. Now theta equals to 245.65. Why did the angle increase, you may ask? Well, the answer is because it wasn't the real angle. The angle is located at 65.65 degrees from the sun to Earth, meaning that the real angle will be 180 plus 65.65, which as you can see is 245.65 degrees. Alexander can now rest in peace knowing that his displacement was of 9.12 meters at a direction of 145.65 degrees.